Welcome back. In the next part of this lecture, we're now going to put some things together and look at strategies for finding limits for functions. So the one thing we've probably noticed up till now is for lots of functions, if you're looking at a point that it's in its domain, you can find limits by direct substitution. So that's always going to be our first limit finding strategy. We'll try to see, does direct substitution work? If you can put in a number and get a number, then good for you. Your limit finding strategy worked. So that's the first option. But of course, you might have things where you can't put in that value. You get something where it's an indeterminate form, usually involving zeros or infinities. So like 0 divided by 0, or 0 to the infinity, or 0 times infinity, or infinity minus infinity. Any of those sorts of forms, those aren't real numbers. So you're going to need to do something to find the limit. And the something is usually some sort of simplification or some sort of manipulation. So in practice, we sort of saw that with the last example at the end of the last video. If you were looking to find the limit as x went to 2 for f of x and you tried to directly substitute, you would have found that that would give you 0 for the numerator and 0 for the denominator. In other words, f of x would be in an indeterminate form as x is equal to 2. But of course, if you did some simplification and canceling, you'd notice that f of x simplifies to look just like this polynomial function where you can evaluate it by direct substitution. So that's sort of the idea here, that we're going to look at a function, we'll have some sort of limit we're interested in, we'll try to do direct substitution, and if it doesn't give us something indeterminate, if it gives us a number, then hooray, we're finished. And if not, then maybe we'll need to do something, maybe some factoring, maybe rationalizing a numerator or a denominator if you've got roots involved, maybe doing a trig identity of some sort. We'll do something along the lines and we'll come up with our limit that way. So let's look at this first example. I'm looking for the limit as x goes to 3 of root of x plus minus 2 minus 1 all over x minus 3. And just on the side, if I were putting in 3 for x, I'd have 3 minus 2 minus 1, and I'd have 3 minus 3. The numerator would give me 1 minus 1, which would be 0, and the denominator would give me also 0. So, of course, that's not a real number. So I know that that means I need to do some sort of work to get it into a form where I can evaluate this limit. So the thing I need to think about is, well, what can I do? And depending on what the thing looks like, that should guide your choice. In this case, I'm looking at this one and I can see that I've got a root in the numerator. So if you have a root somewhere in the numerator or the denominator, you can always rationalize. So that's going to be my plan here. I'm going to rationalize the numerator, so that would move the roots to the denominator, and we'll see if that does anything nice for us. I don't know yet in advance if it is going to, but we'll find out. So since the top was root of x minus 2 minus 1, then I'm going to multiply top and bottom by root of x minus 2 plus 1. And I'm just going to leave the denominator as it is. I'm just going to keep it as x minus 3 times root of x minus 2 plus 1. I'm not going to bother to expand that, not unless I know that I have to. I'm going to also just sort of look at the top, and I know that when I've got something multiplied by its conjugate, I should get first thing squared minus the second thing squared. And so what is that going to do for me here? So I'd have x minus 2 minus 1. I'd have x minus 3. Oh, okay. So now actually I think things are looking up for me, because I notice now I've got x minus 3's in the top and also in the bottom. So I could cancel it. The fact that this is not defined when x equals 3 is not a problem, because again, we're looking at a limit as x approaches 3. And so if you weren't at 3, then the function would be the same as 1 over root of x minus 2 plus 1. So if we're looking at x going to 3, now I ask myself, for this, can I use direct substitution? And the answer is for sure I can. If I put in 3 for x, I'd have square root of 1 plus 1. I'd have 2 in the denominator. This would be a real number, so I feel good about this. I can do direct substitution and say that my limit is 1 over 1 plus 1, which is a half. And so that's sort of the general idea for finding limits from here on out. I'm going to start by checking direct substitution, and if it works, good, and if not, do something, and something that's always guided by what you've got. So in this case, since it was a radical function, I tried rationalizing, and that did it for me. All right, so again, we're going to take a look at this and see what we get just by doing direct substitution. I've got a sneaky suspicion that direct substitution won't help us out here. So if we put in 4 for x in the numerator, you'd have 4 squared minus 16, which is 0. And if you put in 4 in the denominator, you'd have 4 squared minus 6 times 4 plus 8, which is 16 minus 24 plus 8, which is also 0. So it's 0 over 0, definitely indeterminate. So, okay, that means we definitely need to do something in order to find this limit. So in the first one, we had radicals, and so for that, I thought about rationalizing. For this one, I can see it's just a straight-ahead rational function, polynomials on the top and bottom, so I feel like perhaps factoring might be a good choice here. And if I look at factoring, I can see that the top and bottom aren't too difficult to factor. And they factor out with a x minus 4 that's in common for both. So again, we don't care about the fact that x is not that this function is not defined at 4. We don't care about that. We're interested in what's near 4, not at 4. So canceling the x minus 4s is not a big deal for us. And so now we look at what we've got left and ask ourselves, could that function have x go to 4? So let's take a look at that. We've got x plus 4 over x minus 2, and if x goes to 4, the denominator is 2 and the numerator is 8. That's not 0, so we can definitely, 0 over 0, that's definitely a number. We can evaluate that. And so we have 8 divided by 2, which is 4. Okay, this trig function business here, I've got cosine squared times sine on the top, and I've got 1 minus sine squared on the bottom. I'm taking a little bit of a look at this, and I know if you were trying to do direct substitution, sine of pi over 2 is 1. So in the denominator, you'd have 1 minus 1 squared, which would be 0. And cosine of pi over 2 is 0. Sine of pi over 2 is 1. So you'd have 0 squared times 1, which is 0. So this is definitely indeterminate. It's 0 over 0. So I guess we need to do something. And the thing that I'm thinking about doing is using a Pythagorean identity. I know, again, that if you're looking at the denominator, you can see that 1 minus sine squared, and for sure that's the same thing as cosine squared. So I could just use that little trig identity there to simplify. And now I can see that I've got cosines that can be canceled top and bottom. Again, this function is not defined at pi over 2, but we don't care. We're interested in what's near pi over 2, and what's near pi over 2, the graph will look like just sine of x. And we know what happens to sine of x near pi over 2. Its y value gets closer and closer to 1. All right, another nice theorem. This one is useful in a lot of places. The squeeze theorem. This is one where It allows us to find the limits of functions, usually functions that are built on things that are bounded. So as an example of a bounded function, something like sine of x, we know it's bounded because for its y values, they're always between 1 and -1. So if we're thinking about things built from sine of x, there's already this sort of built-in upper and lower bound involved to it. The squeeze theorem says basically if you've got yourself three functions that are always in the order of 1 h of x who is always less than or equal to f of x, so in other words h of x is always below f and f is always below g, so if you were looking at the graphs of them, they might occasionally touch each other. So you could have, for example, f of x being this function and maybe g of x, I'll have g in green. G of x is always above, maybe sometimes touching, but always above it. And that h of x is always below it, maybe sometimes touching. And so that if you were looking for the limit as this function approaches some point c, if the top function has the same limit that the bottom function does, then the middle function also has to have that same limit because it's squeezed in between the two functions. So if you have a top function whose limit as x approaches c is some number, and h, its bottom function, its limit is also approaching that same limit, then the middle function also has to have that same limit. So if h and g both have a limit of L, then the middle function also needs to have a limit of L as well. So for this one, this is sort of a terrible looking function. You've got sine of 1 over x times x squared, and we're looking for the limit as x goes to 0, and definitely direct substitution will not do you any good here because 1 divided by 0 is flat out undefined, so what would sine of that even be? Who knows? And 0 times mystery, not a real number. Who even knows what that is? That's one thing we need to be careful about here, and this is a mistake that people will often make. We're used to in arithmetic 0 times something is always 0, and that is true for real numbers. So if you had that x was a real number and you had 0 times x, that would definitely be 0. But if x was not a real number, so for example 1 divided by 0, that's not a real number, so 0 times that is not going to be 0. So that's a mistake people will make. They'll say, oh, it's 0 times this, which must be 0. It actually turns out not necessarily to be true. So one thing I can say for sure, if I ignore the x squared for now, no matter what's going on with the 1 over x, for sure sine of anything is always between +1 and -1. And that's just the nature of sine as a function. So since that's always the case, if we were interested in what was happening as x going to 0, we could say, well, the limit as x goes to 0 for -1 must be less than the limit for sine, must be less than the limit for 1, which is, I guess, lovely, but that's not super helpful. But what we're interested in is what's going on with x squared times sine of 1 over x. And that's where I say to myself, well, okay, definitely x squared is going to be something positive no matter what's happening, no matter where x is approaching. So if I multiply all three sides of my inequality by x squared, then my inequalities would still hold. So I could say negative x squared should be less than or equal to x squared times sine of 1 over x should be less than x squared times 1. And so now I've got myself three functions. I've got an upper bound and a lower bound. So x squared sine of 1 over x, no matter what x value you want to put in, x squared will always be above it, and negative x squared will always be below it, and x squared sine of 1 over x will always be in the middle. So if that's the case, then we can say for the limits then that the limit as x goes to 0 of minus x squared should be less than or equal to the limit as x goes to 0 of x squared sine of 1 over x. and that should be less than or equal to the limit as x goes to 0 of x squared. Now, I'm going to finish this off in just a minute, but before I do, I want to point out what I need for the squeeze theorem to work. So for me to apply the squeeze theorem, which I'm about to do, I would need that the top limit would need to exist, that the bottom limit would need to exist, and these two limits would have to be equal to each other. So if one of these limits didn't exist, then too bad, you can't apply the squeeze theorem. That's not a valid use of it. So here I'm going to just say to myself, well, let's look at those outer limits and see what happens to them. So number one, I can say for sure that as far as the top one, the x squared, well, that's a polynomial, and so I could look at that by direct substitution. And I could say, well, as x goes to 0, x squared is 0 squared, which is 0. And similarly, you have the limit as x goes to 0 for negative x squared. That limit exists, and its limit is also 0. So this function, x squared sine of 1 over x, it's defined everywhere except for 0. And it's always between x squared and negative x squared. And as we approach 0, the limit for both the upper bound and the lower bound are both approaching 0. So therefore, the thing that's in the middle, the limit that I was actually interested in, that limit must approach 0.